Okay, welcome to lecture number 7. Last time you saw the diffusion equation, and now what I can do is either I can show you how it can be solved. They're just second order ODEs, so all you need to do is put the boundary conditions and you can solve them, Neumann or Dirichlet boundary conditions. So I think it's better for me to move to the second formulation, which is the neutron transport equation. Now, neutron transport equation is a step higher because now we're going to talk about the flux in a number of variables, and you can see that let me introduce these variables for you. So there is going to be position, 3 variables, energy, 1 variable, angle, 2 variables, and time, 1 variable. So how many do we have? We have 7 variables. Now, a complete description in this room of the movement of a neutron requires 7 variables. And the thing in 7 variables is what we call a phase space, right? Phase space. So this is what Boltzmann did. So Boltzmann wrote the transport equation in terms of the distribution function, that where are these molecules at a certain point in time going in a certain angle with a certain speed. So you see, it's such a big issue. And so let me define what I mean by all these things. So we need a good diagram over here. So the diagram is that let's talk of 3D Cartesian space with x, y, and z. Okay. So when a particle is traveling, so let's say that it's traveling in that direction. Now this direction means that it has an orthogonal angle over here and a base angle phi over here. So let me write the diagrams over here, show the vectors. So it's going in this direction, and so omega is now a function of theta and phi. So in fact, mu, if you look at it in one direction, then if you look at the solid angle over here of a sphere, so basically there's the solid angle of a sphere over here. So how do you get this? What is the definition of solid angle? It's the area on the patch of a football divided by r squared. And you can see that this is the small solid angle over here, subtended, let's say, in here, for a patch on the ball looking like this over here. So imagine that this is a football and there's a small area over here. So if this is the radius r, so this becomes r cosine theta, so this becomes r sine theta, so this becomes r sine theta cosine phi, and this becomes r sine theta sine phi. So what do you get over here? You get this thing over here becomes r times d theta, right? And if you move a little bit phi over there, so this becomes r sine theta d phi. So this side becomes r sine theta d phi. So the box over here on the football has an area which is the product of the length times the width. So it's r squared sine theta, r squared sine r sine theta d phi, right? And so this inside becomes r sine theta d phi. So r sine theta d phi divided by r squared over here. And there's a d theta over here also. So so these cancel out. So this becomes sine theta d theta times d phi. And I can write this as d mu times d phi if I define, if mu is defined to be cosine of theta. Right? So basically, here's my definition of solid angle. It's d omega is d mu times d phi. Okay, so this is how things are moving. And so I'm going to write the transport equation for a neutron which is moving over here in this solid angle. Okay, now let's see how we are doing with time. Okay, so let me just continue because it will break the momentum if I stop over here. Okay, so basically, again, the simple thing that we did for diffusion, that we write a balance equation that in is equal to out. Now, what is the leakage? The leakage term is the out term. So let's say that it's omega dot grad phi, right? Omega dot grad phi. Just like before, we had d grad phi. So now we have this streaming term, which is this. And how many are going out? So if we have a total cross section over here, then the total cross section at some position RE at some time t times phi RE omega t. And okay, let me show this over here. So that's what is going out. And how much is coming in? Well, how much is coming in from scattering taking place somewhere else, right? So it's somewhere else in some other energy, some other angle going to R E omega at t times phi R E omega t over here and integrated over all the initial variables. Okay, so let me say the d p prime, phase space p prime, plus whatever source you have in the phase space of interest. So this becomes your neutron transport equation in very simple, straightforward terms. Now, what does it look like? So let's write it in a slightly more elegant form. So let's say that I'm just interested in one angle over here. So mu, let me say that it's just one angle. So d phi by dx. Okay, let's just talk of x plus sigma t x e. And let's get rid of the angle part over there. So in other words, let's say that I've integrated over everything, and let's say I'm not interested in time also. So x e mu. Okay, so there's a mu over here because I showed you this time that d omega is d mu times d phi. So this becomes the left hand side, and the right hand side becomes the in-scattering term. So sigma s at x, let's say it's at the same x, and e prime to e. And now let me write omega dot omega prime, because collision doesn't depend on the two angles. It depends on the dot product between the two angles. So this multiplied by x e mu over here plus a direct x e mu. And this would be d e prime and d omega prime. Okay, so let's put an e prime over here. So what does this look like? Now this looks like an integral differential equation. So this looks like an integral differential equation. And it is one of the easier forms of the Boltzmann transport equation. Now, this also is a conservation equation. And Boltzmann's equation is so general that you can actually construct moments of the Boltzmann distribution function. So this is the zeroth moment, which is the continuity equation. Now the first moment would be the conservation of momentum. The second moment would be the conservation of energy, and you could gradually go up to higher moments where you could use them to reconstruct the distribution function. So sometimes you don't know the distribution function, but you know the area under the curve, you know the variance, you know the kurtoses, you know a number of mathematical properties, and you try to put them together and construct the distribution function. Now, it is the distribution function that you are after, because then you know everything about molecules in this room. Just like here, it is the flux that we are after. So just take a closer look at this. So I don't want to go into the solution right now, that I'll talk separately about. Right now, just look at it and see that it's not such an easy thing to solve. And that is why there are no exact solutions of the neutron transport equation. People did try them earlier in the day, in the 1930s, 1940s, Wiener, Hopf, Chandrasekhar, and because the field those days was astrophysics. So they were trying to study stars, space, the albedo of the Earth, that what fraction of light reaching the Earth is reflected back. And Chandrasekhar was a person who worked with Einstein. Now his H function, if you see the books, for example, by Bell and Gladstone, his H function, which is obtained via a transcendental equation, can be used to obtain the albedo, the reflectivity of any half space. So Wiener-Hopf solved this equation for simple, very simplified conditions such as infinite space, semi-infinite space, finite, not so simple, and I've not even put the fission term as yet. So when I put the fission term in this, you'll see that this thing becomes just not solvable. And so numerical techniques are used to solve the neutron transport equation. Now today's nuclear reactors, nuclear systems require a solution of the transport equation, they require a solution of the diffusion equation. And these are not, of course, easy things. So I'll discuss the solution of this with you after I discuss our third formulation. So just hold on for the third formulation, which will be fun because there we'll talk about Monte Carlo simulation, which is today's game because we've got very high performance computing. So just wait till the next lecture. I'll introduce Monte Carlo for you. Then we've got three formulations. We'll discuss them together. We'll discuss their solutions. And then let's see how we can go forward. Thank you so much.